So welcome to the lectures of power system dynamics and control. So yesterday we were discussing the various subtransient and transient reactances, d-axis and q-axis subtransient reactances and transient reactance, and also we derived the expression for open circuit d-axis and q-axis time constants, transient and subtransient time constants. So we're about to derive the equations. We'll do this in this class. So what we did that we derived reactances in the previous class, and also we derived the open circuit d-axis subtransient time constant, that is 1 by omega base r1d xl1d plus 1 by 1 of xmd plus 1 by xl1d. So this is your TD double S. And also we have derived subtransient time constant in quadrature axis. And that is this. By considering the quadrature axis equations, we can derive. Finally, the transient time constants also can be derived by only taking additional assumption of current in the damper winding, that is I1d in the d-axis should be 0, and in q-axis I2q should be 0. And considering that, we will have very simple equations of flux linkage in the field, and considering the VFD equation, the voltage equation in the field, we can easily derive the transient time constant, open circuit transient time constant associated with d-axis, that is xfd by omega base by rfd. And similarly, we can derive the q-axis open circuit transient time constant, that is x1q by omega base r1q. Right? Considering the q-axis equations, we can derive. And few new variables we defined, that is eq dash, that is equal to xmd by xfd psi fd, and ed dash, that is equal to minus of xmq by x1q psi 1q, and EFD is xmd by rfd into VFD. So then we wrote the equations of flux linkage in the field winding, that is field and damper winding, psi fd and psi 1 in the matrix form. And from this, we can eliminate IFD and I1D, taking the inverse of this matrix, xfd, xmd, xmd, x1d. And after finding from this, we can find the separate equations for IFD and I1D. Up to this we have done. And IFD, I1D, we can write this. Now each of these terms, that is, each of these terms is x1d psi fd by delta, xmd psi 1d by delta, x1d minus x1d xmd minus xmd square by delta. All these terms will find the expression in terms of time constants and also the new variable we have defined in the last slide. Time constant and the reactances and and also the new variables we have seen. So each of the term will express now, right? So each of the term will divide. Delta is the determinant of this matrix. This is the determinant of this matrix, right? Now if we'll evaluate delta, delta will be xfd x1d minus xmd square, determinant of this, right? And by expanding, just substituting xfd equal to xlfd plus xmd and x1d equal to xl1d plus xmd, we'll find out this expression, right? So that will be delta. Now, this is the equation for IFD and I1D we derived, right? Now we'll evaluate each of the terms and we'll express each of the terms in terms of subtransient and transient reactances and the defined new variables. Now, the first term for IFD equation. Now we'll consider the IFD equation. So IFD equation first term is 1 by delta x1d psi fd, right? So I am considering 1 by delta x1d psi fd. Now this little adjustment if we'll do, if I'll multiply xfd in both numerator and denominator, then it will become xfd x1d by xmd into delta, and also xmd in both numerator and denominator, then it will become xmd xfd psi fd. So xmd xfd psi fd is a term we have derived. We have assumed a term for this new term, new variable, that is eq dash, right? So we'll substitute directly xmd by xfd into psi fd is eq dash. Now we'll expand the delta term. So it will be 1 by xmd into, so xfd by x1d by delta. If we'll write this, it will become 1 plus xmd square by delta, right? So xfd by x1d by delta will be equal to 1 plus, because from this expression I can say, we'll write it from here, xfd x1d will be delta plus xmd square, right? So now delta plus xmd square, if we divide delta, it will become 1 plus xmd square. I can write this here. xmd x1d will be equal to delta plus xmd square from this equation, right? And now if I'll write xfd x1d divided by delta will be equal to 1 plus xmd square by delta, right? So that is what here it is mentioned. You can see here this term xfd x1d by delta is nothing but 1 plus xmd square by delta, right? Now if we'll expand delta and substitute, and finally I'll substitute the transient reactances, dx is transient reactances, I'll find 1 plus xd minus xd dash into xd dash minus xd double dash by xd dash minus xls whole square. So it is eq dash. This is also eq dash, right? It will remain as it is. So now your expression will become 1 by xmd, 1 plus xd minus xd dash minus xd double dash. So now I have expressed this equation in terms of transient reactance, subtransient reactance, and also the steady state reactance, right? Divided by xd dash minus xl square, right? Similarly, I can write the second term. So this is explained here very clearly. xmd square by delta can be written as this, okay? And eq dash is xmd by xfd into psi fd. Now considering the second term is your xmd psi 1d by delta. So xmd psi 1d by delta is 1 by xmd. So it will remain as it is. And just I'm dividing and dividing and multiplying xmd, so it will become xmd square by delta. So xmd square by delta, you know, this I can substitute instead of xmd by delta, right? Now substituting this in case of xmd square by delta, so your second term will become this, right? Now coming to the third term. Your third term is x1d xmd by xmd square minus xmd square divided by delta, right? So x1d minus xmd minus xmd square by delta into id. So now you know xmd square, this will become, if we'll expand this and multiply, and we'll have equation xlfd into xl1d minus, sorry, it will be xl1d into xmd, and in the numerator and denominator I am multiplying xlfd both in numerator and denominator. And then this expression will become 1 by xmd into xt minus xt dash, xt double dash minus xls by xt dash minus xls into id. So where xlfd I can write as this, xt dash minus xls divided by xt minus xt dash xmd, and xlfd into xl1d into xmd by delta, I can write this, right? So both the terms, if I divide, I'll get xt minus xt double dash into xt double dash minus xls by xt dash minus xls. Okay. So 1 by xmd will be another term, it will remain, right? So now we have written each of the terms of IFD in terms of reactances of the generator. Steady state, transient, and subtransient reactances, right? Similarly, I can write each term of I1D in terms of reactances, okay? Like subtransient, transient, and steady state reactance. So by writing this, first term is your XMD psi FD by delta, right? Just a few adjustment, XFD by delta into XMD by XFD psi FD, that is EQ dash, and XFD by delta is nothing but it is XT dash minus XT double dash by XT dash minus XLS square. Okay. Then here we have seen this equation, XFD by delta will be equal to this, EQ dash will be this, right? And then the second term is psi XFD psi 1D divided by delta. So the same way I can write XFD by delta, I can substitute here, and psi 1D will remain as it is. So instead of XFD by delta, I can substitute XT dash minus XT double dash by XT dash minus XLS whole square, right? Then the third term is 1 by delta xfd xmd minus xmd square into id. So it's just few adjustments. I can expand this equation as xlfd plus xmd, and my remaining term will be xlfd into xmd by delta into id, and this I can write xt dash minus xt double dash by xt dash minus xls. Okay. So now we have we found that each of the terms of IFD and I1D in terms of the reactances and the new variables we have defined. And now if we'll replace each term in IFD and I1D as derived above, we'll have this expression. So your IFD will become this. Finally, we'll get this little adjustment and manipulation. We'll have 1 by xmd EQ dash plus xt minus xt dash into id minus I1D. Okay. Then for I1D, the equation will be xt dash minus xt double dash by xt dash minus xls square whole into EQ dash minus EQ dash plus xt dash minus xls into id plus I1D. So this will be equation for I1D, right? Now similarly, we can write the equation for, okay, so before moving ahead, we can substitute IFD and I1D in the equation of psi d. So psi d will look like this. If we substitute IFD and I1D equation in psi d expression we know, that is minus xtid plus xmd IFD plus xmd I1D. So instead of IFD and I1D, I can substitute the previous equations, whatever we have derived, right? This substituting will find this expression. Minus xt double dash id plus xt double dash minus xls by xt dash minus xls into eq dash plus xt dash minus xt double dash by xt double dash minus xl is psi 1d. So we got the expression for psi d. Similarly, we can get in similar way the q-axis flux linkage equations along with the current I1q and I2q can be expressed as this. So we can write. So here we have derived the expression for I1d, IFD, I1d in the d-axis rotor current, and the flux linkage equation psi d, right? And similarly, we can write in the q-axis psi q. We can find the expression just by manipulating, and we'll have also expressions from I1q and I2q because we'll substitute these equations I1q and I2q in order to find psi q. Okay, so similar equations we get for psi q, I1q and I2q. Just replacing the subtransient and transient reactances across the q-axis, right? And these are the parameters we know. We have defined this variable. CQ dash is xmd by xfd psi fd. Ed dash is minus xmq by x1q psi 1q. EFD is xmd by RFD into VFD, right? Now your time constants, your subtransient and transient time constants, if we'll represent just writing this subtransient d-axis time constant in terms of the reactances, we can write it very easily. Just little manipulation, xmd xlfd by xmd by xlfd plus xl1d. Just by adding this term with this, we will get this expression. And then this expression, we know this is nothing but is equal to delta. So we'll get 1 by omega base r1d delta by xfd. So if we'll take delta to the denominator, we'll get 1 by xfd by delta. So for xfd by delta, we have already one expression, that is xd dash minus xt double dash by xt dash minus xls squared. So just substituting, we'll get this time constant in terms of the reactances, transient and subtransient reactances, right? Similarly, for q-axis, I can write tqo dash double dash, that is q-axis open circuit subtransient time constant will be equal to 1 by omega base r2q and 1 by xq dash minus xq double dash by xq dash minus xls square, right? So now we wrote this. Wherever we have these expressions, we can immediately substitute TDO dash and TQ dash, TQ double dash, TDO double dash and TQ double dash. So now we have the final equations. Just little manipulation. We have derived this equation from the starter voltage equations. Already we have derived, right? This is a set of differential equation, and now these equations can be derived from the rotor voltage equations. That is the equation for VFD, V1D, V1Q, and V2Q. Just by manipulation, we'll get these equations by substituting the time constants and various parameters. Okay, we'll find the expression for another set of differential equation, right? Next, we have this is your electromechanical equation, that is swing equation, right? Already we have seen this. It is also existing for, because this is your mechanical torque. This is the torque with friction and windage. And this is your electromagnetic torque, which we derived in per unit, that is psi d iq minus psi q id, right? Okay, now this is your change of speed, d delta by dt. Okay. This is a swing equation. Now these three equations we have derived, that flux linkage equation, already we derived these three equations, two equations, and similarly IO can also be derived, right? So now we have complete set of equations for a generator which actually describes the behavior of generator. This is a set of differential algebraic equation. We can see these are the differential equations, and this set is your algebraic equation, right? So we have set of differential algebraic equation which actually describes the behavior of the generator, synchronous generator. Therefore, we can say this is the mathematical modeling considering the dampers, the field winding, everything for a generator, right? Now the modeling of the generator is complete. Overall, it is complete. It took a long period to finally arriving at a particular model. So this is your model considering various parameters like your subtransient, transient, d-axis, q-axis reactances along with the steady state reactances and also the open circuit transient, subtransient time constants, right? Okay, now this is your set of DA, differential algebraic equation representing the generator. So now we'll go to other components of the generator like your exciters and the turbines. So first we'll see your exciter, modeling of the exciter, then we'll go to turbine and governor system. So before moving ahead, let us see what is the exciter and how it actually helps in system dynamics. Okay. Now I can see here we have generator and power system, which generator is connected to the power system, and the generator is having starter and rotor, and the rotor we have field winding of the generator, and starter of course provides the external output to the power system. And what is the role of exciter? Exciter in fact provides the current to the field winding of the generator. So that is the role of the exciter. Now you can see here the voltage transducers here actually measures the terminal voltage of the generator, and it in fact gives the signal to the voltage regulator, and by that way voltage regulator gives signal to the exciter. And similarly we have limiting and protecting circuit which actually limits the generator exciter limit and the turbine limit. It limits the generator exciter limiting capability. So it also gives signal to the voltage regulator, and through the voltage regulator it limits the excitation of the field, under excitation and over excitation. Then the rate feedback, which we have seen, this rate feedback actually we can see this is the feedback signal is taken from the terminal of the exciter to the voltage regulator. It in fact helps in stabilizing the exciter. That means to improve the stability of the exciter system only, right? So it helps in stabilizing the exciter. Now the power system stabilizer, it in fact stabilizes the oscillations, local and inter-area oscillation, low frequency oscillations. And in fact, it measures the signal, local signal from the generator. And from the local signals are fed to the power system stabilizer, and it is fed to the voltage regulator. Through that, it gives signal to the exciter, and by that way, it stabilizes the low frequency oscillations. So this concept of power system stabilizer is well known and is PSS, and this in fact will be taught in your small signal stability classes later, and it will be taken by Professor Shiva Subraman. So now we'll see the exciters. How these exciters, what are the different types of exciters? The exciters generally, nowadays we have three types of exciter: DC exciter, AC exciter, and static exciter. What is DC exciter? In this type of exciter, a separately or self-excited DC generator driven by a motor or connected to the same shaft as that of the main generator rotor is used. So, as the name itself suggests, that this DC exciter is a DC generator. It can be a separately excited DC generator or self-excited DC generator, and it can also be driven separately by a motor, or it can be directly installed on the shaft of the main generator. In case of separately excited DC generator, the field winding of the DC generator is energized through the permanent magnet AC generator, the three-phase output of which is converted to DC through the rectifiers. Okay. So the permanent magnet AC generator, actually, the three-phase output of this generator, in fact, feeds the field winding of the DC generator. So the example of DC excitation system is IEEE type DC1A excitation system. This is the standard IEEE system. Generally, when we model the generators, we take these standards. This type of excitation was widely used up to 1960, but nowadays AC excitation or static excitation is being used. For older generating stations where DC excitation is still used, the voltage regulator alone is replaced with electronic regulator. So previously the voltage regulator was mechanical arrangement. So therefore, nowadays the electronic regulators are replacing the voltage regulator, and this DC excitation, of course, working in some old generating stations. Now AC exciter. In this type of exciter, the AC generator, whose armature is mounted on the same shaft as that of the main generator, with its field stationary, is used for supplying field current to the main generator field winding. Okay. And the output of the AC exciter generator is converted to DC through the rotating rectifiers, as the armature is now rotating at the main generator rotor speed, and the output is directly connected to the main field winding. Already we have discussed these concepts previously when we started the generator modeling, right? Then the field of the AC exciter generator itself is energized through a pilot permanent magnet AC generator, whose three-phase output is converted to DC through some rectification arrangement. So example of this is IEEE type AC1 exciter. This is a standard IEEE excitation system. Then static exciter. In this exciter, the output of the main synchronous generator is converted from AC to DC through static rectification, and then the output is supplied to the main generator field winding through the slip rings. So this is very simple. For like we'll get synchronous, it will converted from AC to DC and through the static rectification. That means some rectifier is connected and we are getting AC supply from somewhere else, or we can get it from main generator itself and we'll rectify it and will feed to the field winding of the main generator through the slip rings. So the example of this IEEE type STA1, this is the standard IEEE static exciter, right? Therefore, it is IEEE type ST1A. Okay, the components used in the excitation system, that is voltage transducer. So voltage transducers, as I told, the voltage transducers measure the three-phase terminal voltage through the potential transformers and convert them and filter them to DC, which is compared with the reference voltage, And the error signal is used to control the main exciter field winding current through the exciter. Voltage regulator. So the voltage regulator can be of magnetic amplification type or digital amplification type. At present, digital amplification is widely used. Voltage regulator amplifies the error signal generated by the voltage transducers, and the output of the voltage regulator is used to control the pilot excitation, thereby controlling the main generator field winding through the DC-AC excitation system. Right? So the voltage regulator plays a very important role. Limiting and protection circuit. Limiting and protection circuits are used to limit main generator field winding current, overexcitation, underexcitation, terminal voltage, volts per hertz, etc. Right? Rate feedback is used to stabilize the excitation system, and we'll also discuss the modeling of all these components. Then power system stabilizer, it is used to damp the power system oscillations through the excitation system. So power system stabilizer will be taught during your small signal stability. Okay. So this is all about your little bit. We talked about the excitation system, and the detailed modeling we'll see from next class onwards for the excitation system, and then turbine and governor system. And finally, we'll see the load modeling. Okay, we'll stop here. Thank you very much. We'll talk more on the excitation system modeling in the next class. Okay, thank you.